Hello, we will discuss today resistance and resistivity. For example, these are two materials. One is copper, the other is glass. And let's suppose they have the same geometry, means they have the same length and they have the same cross-sectional area, for instance. But if you connect these two materials separately to the battery by providing the potential difference to these two materials, the current appearing in these two materials will be different. So the question arises why it happens so. Despite their same geometry, the current appearing in these two materials is different, while given the fact that the same potential difference has been provided to both. So the answer is that these two materials have intrinsically a characteristic due to which the current appears differently in both cases, and that characteristic is called resistance. So we define the resistance as V over I, where V is the potential difference provided to a material and I is the current appearing in that material as a result. So this is the basic definition of resistance. These are some resistors shown in this figures, and the unit of the resistance is ohm, and we define 1 ohm, which is denoted by this symbol, 1 volt per ampere. 1 volt, 1 ampere, so this is 1 ohm. So a conductor whose function is in a circuit to provide a specific resistance is called a resistor. So this is the definition of resistor. In a circuit, we represent the resistor by this symbol, which is shown here. Now, what is resistivity and conductivity? Resistivity. We define the resistivity as that it is equal to E over J. This is the basic definition of resistivity, which we call rho. And E is the electric field in a conductor and J is the current density in that conductor. The unit of resistivity, it is ohm meter. How does it come? The unit of electric field is volt per meter. The unit of current density is ampere per meter square. 1 m in denominator will cancel out with another m in numerator, and this will become V over A meter, and V over A is ohm, so ohm meter. So we can write this equation in terms of vectors, that electric field will be equal to rho J. So just rearrange this equation. Rearrange equation number 2, you will get equation number 3. Now conductivity. Conductivity is simply a reciprocal of resistivity. We simply write as it is. So the equation, this equation, equation number 2, can be simply written as J is equal to conductivity E in terms of vectors. How will we calculate resistance from resistivity? And what is the difference between resistance and resistivity? So here we state an important point, just note it down. I will explain it further. That resistance is a property of an object, while resistivity is a property of a material. So what is the difference between an object and a material? And what is the difference between resistance and resistivity? Let me explain it. For example, this is a conductor whose length is capital L, and a potential difference of V has been applied to the two ends of the conductor. A is the cross-sectional area of this conductor, and as a result of the potential difference, current appears, which has been shown flowing from left to right. So this current is basically driven by potential difference. We know that electric field is equal to V over L, and J is equal to I over A. J is the current density, I is ampere current, and A is the area. We also know that resistivity is equal to E over J, electric field over uh, current density, and rho is the resistivity. So in this equation, just substitute the values of E and J. So we know the value of E from here, the value of J from here. Just substitute these two values in these equations, E over J. So this will become V over L divided by I over A. Now this way, this term Y V over I, this is basically resistance. So you can substitute V over I with R and rearrange these equations. You will get R is equal to rho L over A. Now look at this result. It is very interesting. So what do you see? You see that resistance depends upon rho L over A. Okay, the first thing you note that we started from resistivity and we acquired an equation for resistance. So we calculated basically resistance from the resistivity. Okay, so what does it imply? For example, these are two copper conductors. One is more length than other. The red one has more length than the blue. Now look, they are of the same material. Both are copper. So they will have the same resistivity, because resistivity depends upon the material, which material it is. The resistivity of the copper is different from the resistivity of the glass. But the resistance varies within a material as well. What does it mean? It basically means that the geometry of these two copper are different, no matter if they are both of them are copper, but their resistance will be different according to these equations, because one has more L than the other. So these two copper have the same resistivity, but they have the same uh, but they have the different resistance. This is very important, just note it down. Next is how the resistivity changes with temperature. So we write in the equation rho minus rho naught is equal to rho naught alpha T minus T naught, where we write, we can show this equation in the graph like this, where T naught is the room temperature, which is normally 293 Kelvin, and rho naught is the resistivity at that temperature, which is normally 1.69 into 10 to the power minus 8 ohm meter for copper. For another material, of course, it will be different. And alpha is the temperature coefficient of resistivity. So what do you see from this plot? It basically shows that with increasing temperature, the resistivity of a material, it increases more or less linearly.